The next part of our modern physics unit is nuclear energy. This gets into nuclear physics. If you were part of our guest speaker presentation earlier this week, you learned a little bit about nuclear physics already, and she did explain some of the really neat things that nuclear engineers are doing out in the real world. So this is a pretty neat unit. We're going to review some of the things that hopefully you already know about the atom. So nucleons, those are the particles that are found in the nucleus, right? The nucleons are the protons and the neutrons. The other thing you have to remember about the atom is the atomic number. Okay, so the atomic number, if you think about the periodic table, the atomic number tells you the number of protons that are in the nucleus. Okay? The symbol for the atomic number is a capital Z, right? That's just when you're looking at a generic atom, right? The atomic number is a Z. The other thing to remember about the atomic number is that this is what makes the atoms different, right? The number of protons in the nucleus makes the atom that atom. Right? The other thing you need to remember is the mass number, right? So the mass number is the total number of protons plus neutrons, right? The symbol for mass number is a capital A. So again, in just a generic atom that you're looking at, the mass number would be a capital A, kind of a placeholder. Right. Now, the thing to remember here, and the really kind of important piece of this unit, is that there must be a force that holds the nucleus together. So you have protons, which are positively charged, and neutrons, which are neutral. So they are held together by the nuclear force. All right? So the nuclear force is something that holds the nucleus together, and it acts over a very short range. Right? So it's a very, very strong force, but it acts over very small distances. And if you think about the atom and the nucleus of an atom, it's a very, very small quantity, small particle that you're looking at. Underneath that, you see a carbon atom, right? And so this is what you would see, the symbol that you would see. And from this, you'd have to pull out information. You'd have to pull out the atomic number, and then you'd also have to pull out the mass number. And so looking at this, right, this is carbon, you see that you have an atomic number of 6, which tells you the number of protons. You have a mass number of 14, which tells you the number of protons plus neutrons, so how many particles are in the nucleus. But from that, you can also determine how many neutrons this carbon has, right? And so you take the mass number minus the atomic number, and that gives you the number of neutrons that are here. Okay. So the nuclear force, okay, again, this is what holds the nucleus together. This acts over very, 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 very small distances, right? So the distance is less than 10 to the negative 15 meters, right? So that's extremely small. The other thing to know about the nuclear force is that this is the strongest force known in nature, right? So the nuclear force, these forces that hold things together, are the strongest forces known. Right? Just as a frame of reference here, it's 2 orders of magnitude bigger than the electrostatic force. So the electrostatic force is a pretty strong force, right? That's the force that holds charged particles together or causes charged particles to be repelled. But the strong nuclear force is 2 orders of magnitude stronger than the electrostatic force. Right? So it does say here that the nuclear force is also called the strong force. Right? It is the strongest force in nature. It holds that neutron together. So one thing we do have to talk about is the mass when we are talking about nuclear energy and nuclear physics. Okay? Atoms, when we talk about atoms, we use a different unit to measure their mass. Right? Now, in chemistry, I think you were exposed to this, right? 1 atomic mass unit, AMU. Physicists are kind of lazy, so we don't use 1 AMU, we use 1 U. right? And so instead of saying atomic mass number, physicists call this the universal mass number, right? So one universal mass unit is equal to 1.66 times 10 to the negative 27 kilograms, right? And that's roughly the mass of a proton and a neutron, right? It's a little bit smaller. Right? This is on the front of your reference table in a different form, right? So just be aware of this. This is the number you may want to write down. But the mass of a proton in universal mass units, right? You could convert because the mass of a proton is given to you on the front of your reference table. You could convert from kilograms to atomic mass units. Right? So mass of a proton is approximately 1.0073 universal mass units. Mass of a neutron is approximately 1.0087 universal mass units. The mass of an electron, very, very small, right? 0.0005 universal mass units. And then the mass of carbon, right? Mass of carbon-12 is 12 universal mass units, right? So this brings us to talking about Einstein's famous equation here that I know all of you know. We haven't studied it yet, right? But that is E equals mc squared. So Einstein was the one who investigated the relationship between the mass and the energy, right? And so all mass has energy, and essentially what this means is that energy is mass and mass is energy. Okay, so Einstein was the one who came to the conclusion that mass is energy, but we just use different units to measure them. Right? So in nuclear science, mass is often given in energy units because mass is energy and energy is mass, right? They go hand in hand. So instead of saying, the mass of a proton is blank number of kilograms, in nuclear science, if you are interested in nuclear science and you become a nuclear scientist, you will see energy and mass in the same units, right? Like mega electron volts. Right, so remember, electron volts are units of energy that we started looking at when we looked at circuits, right? An electron volt. So now we're looking at mega electron volts. So remember mega, I did write it on here. Mega is the prefix for 10 to the 6. So mega electron volts are huge amounts of energy. Right, so there you have E equals mc squared. So E is your energy, as we've always known. M is your mass, and C is the speed of light in a vacuum. So Einstein was the one who came up with this relationship that the energy is equal to the mass times the speed of light squared in a vacuum. Right? So things to remember here. Mass and energy together are always conserved, but it may be converted back and forth during nuclear reactions. So that means that you may have some mass that essentially goes missing because it's turned into energy. And you also may have some energy that looks like it goes missing, but it has turned into mass, right? So you will see that the total mass and energy together are always conserved. So the mass plus the energy of the whole system will remain the same, but the mass may change depending on the reaction that occurs. Right? And that's because you have to either put energy in to get the reaction to occur, or energy has to come out to get the reaction to occur. Right? So one universal mass unit, so something similar, something close to a proton, is equal to 931 mega electron volts. Right? That is on the front of your reference table. So one universal mass unit is equal to 931 mega electron volts. So you'll notice we have a mass over here on the left-hand side, and that's equal to a certain amount of energy, right? That's Einstein's famous equation here. Mass is energy. So let's look at this. Nuclear mass, right? So the total mass of a nucleus is always less than the mass of the nucleons that made it. Okay, read that again. The total mass of a nucleus is always less than the mass of the individual nucleons that made it. So for instance, if a nucleus has 2 protons and 2 neutrons, there's a certain amount of mass. If you add 2 protons plus 2 neutrons, you get a certain number. But then if you combine those 2 protons and 2 neutrons and get them to be a nucleus together, the mass of that nucleus will be less than the calculated mass. Right? We call this the mass defect. Right? So this is mass defect, the mass of the nucleons minus the mass of the nucleus. So the nucleons are the number of neutrons and protons, their mass added together. But then the mass of the actual nucleus itself is different than that. And so you have essentially missing mass there. And that missing mass equals the energy required to bond those nucleons, right? So to bind the nucleus together requires energy. So we call the missing mass the mass defect, and it's also called the binding energy because that mass that's missing equals the energy that's needed to keep the nucleus together. So the binding energy is the energy equivalent to the mass defect. And that's why you need that conversion of 1 universal mass unit equals 931 mega electron volts. Okay? So this binding energy is the energy that you need to put in to break the nucleus apart. Right? So lots of different things going on here. The missing mass is called the mass defect. You can convert that missing mass to find the binding energy. And that's the amount of energy that you have to put into the nucleus to separate the nucleons. Right, so here's an example. What is the energy released when carbon-12 is formed? So to make a carbon-12 atom, carbon-12 has 6 protons and 6 neutrons. So I'm going to find the mass of those nucleons together. So 6 protons, the mass of a proton is 1.0073 universal mass units, right? So I have this here. The mass of a neutron is 1.0087 universal mass units, and there's 6 of those. So 6 times each of those, add them together, you get 12.096 universal mass units. However, you should know that the mass of carbon is 12, right? So if you look at the mass number for carbon, is 12. So you see there's a difference here, right? So the mass of the nucleons individually gives me 12.096, but the mass of the nucleus of carbon is 12. So there's a difference there. The mass defect is 0.096. Now the question is, how much energy is this? So we need to convert this mass defect, into the amount of energy. So this tells me that the binding energy is 0.096 universal mass units, right? Because the binding energy equals the mass defect. So I'm going to convert this amount of mass into energy. And here's my conversion, right? 1 universal mass unit equals 931 mega electron volts. So I get 89.376 mega electron volts. Right? If I just take the mega out, right, that means times 10 to the 6. So I get 89,376,000 electron volts, or excuse me, 89,376,000 electron volts. And then typically you will be asked to convert that to joules, right? So I did that here for you. 1 electron volt, again, on the front of your reference table, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Do that conversion. And so you can see this measured in joules now, which maybe is a little more realistic to you, right? So you have 1.43 times 10 to the negative 11 joules. So that's one example of using mass defect to determine how much energy that mass is. Okay. Binding energies are usually in terms of energy per nucleon, with the highest at a mass number of around 60. So for elements above carbon, energy is approximately 8 mega electron volts per nucleon. Okay, and so what do I mean by that? So you know that there are 12 particles in the nucleus of carbon, right? 6 protons, 6 neutrons. So there's 12 particles there. And we just determined that the mass defect, the binding energy, is 89 mega electron volts. And so if I take that amount of energy and divide by the number of particles, you get 7.4 mega electron volts per nucleon. Right? So that means that each neutron and each proton is roughly equivalent to 7.4 mega electron volts in that atom. Right? And so for anything above carbon, right, with a mass number greater than 12, energy is approximately 8 mega electron volts per nucleon. Just something interesting to know. Okay. The other thing to know is that when you increase the binding energy, that means you have a more stable atom. Okay, so the binding energy is the energy that you need to put into the nucleus to break it apart. And when you have to put tons of energy in to break that nucleus apart, that means it's pretty stable and it's going to take a lot of energy to break that bond. Right? So the more binding energy you have, the more stable that atom is.